The Chapter 3 test. All right, let's go through it here. First, use the information above to write one true statement about the absolute change. Absolute change means what is the difference? And if you look at these, there's a difference of 50 cents. Now, to write a statement, a sentence using that, you can say the shares increased by 50 cents okay, or the shares are 50 cents more now, or something like that. Okay. Number 2, use the information above to write one true statement using percentage as a fraction. So we can make a fraction two different ways. We can go 2475 divided by 2525. If we do that, 24.75 divided by 25.25, we get that 98 in percent times 100 would be 98.0%. Now to write a sentence, the reference in here is the current price, the earlier price and the current price. So this is saying we've referenced to the current price. And we use the word of, and since it's the current price in the end, of the current price. And what do we say relative to that? Well, the old price is 98.0% of the current price, or the price now, something like that. Now, if I divided it the other way, making the fraction the other way around, I would have gotten 25.25 divided by 24.75. I would have gotten 101.02, or 102%. And now this is the old price, and so of the old price, and it's 102% of the old price, the end, and the new price, or the current price. Is 102% of the old price. Again, what you put on the bottom has to be what you end with. Of is the way you use it as a fraction. Okay. Use the information provided to write one true statement about percentage as a change. So the change was 50 cents. So now you can take the 50 cents and divide it by the old price, and that would give us 2.0%. Now to write a sentence using that, you end again with the 24.75, the old price, and this is either more or less, and we're going to put what we don't have on here is the new price is 2%, 2.0% more than the old price. Now, if I'd done it the other way, 0.50 divided by the 25.25, I get 1.98%. But now it's the current price. And that's the reference, so that's got to go in the end. New or current. And we have 1.98%. And since we used the new price, it has to be the old price is 1.98% less than the new price. Okay? Hopefully you're getting the idea of the reference. Goes on the bottom and ends the sentences here. That's what I wanted you to get out of that. Similarly, I wanted this, I forgot to say in percent. Make your statement comparing the prices in percent or using percentages. Okay, so there's a change here, and the difference between those is 16 cents. So if I do 1/6 comparison, you use the difference over one of these two. So if I do over the 3.19, then I've got to end my sentence with Warrior stop. Price at the Warrior stop. And 0.16 divided by 3.19 is 5.0%. So 5.0%, and if I've used Warrior Stop there, then it must be the other one, Safeway. So the price at Safeway is 5% more than the price at Warrior Stop. And if we're going to do the comparison the other way, 0.16 divided by the 3.35, which turns out to be 4.77, 4.8. If I'm putting the 3.35, that's the price at Safeway, so I have to end with price at Safeway, 18, that. And we have to go back here and say the price at Warrior Stop is 4.8%, and since the Warrior price is less than that, so less than the price at Safeway. Once again, emphasizing that your reference value ends your sentence. The reference ends your sentence. Okay? And you put the difference above these. Okay. Allison scored 22% better on her second test than on her first. So, better than on her first test. So the first test is the base. So that's 100%. And she scored that plus 22% of that more than that. So she increased her score to some percentage of her first score. So we want to take the new score, which was 122%, compared to her old score, 100% of her old score. Now, it doesn't mean she had 100%. Whatever the score is, that total is there, and 122% is on the numerator. And this comes out to be a percentage that says 122 divided by 100, which is 1.22%, or 122%. Simply 22% better, so she had her old score of 100% plus 22% better. Desiree took a 2% pay cut, so she took a cut from her original pay. So original pay, her new pay is 2% less minus the 2%, which means that she's left with 98%. And so that's of her original pay, she's got 98%. Now, most people did these two well. That's the next ones that cause people trouble. Men earned 17% more than women. So we end with women. Women are a reference. So that's 100% of whatever the women pay was. Men get all of that plus 17% more. So they get a total of 117, and we could just say, if women were paid $100, the men were paid $117. So women earn what percent of? So we have to, of means we're going to divide what men earn. Well, that's going to be our denominator, so that has to be the 117%. And our numerator has to be what the women make. That's 100%. Could be $100 and $117. That in percent is 100 divided by 117. So that's 85.4%. So women earn 85.4% of what men earn. Now you can make up a salary. You could make it be $100, and then the men make $117. You could do it in dollars if you wanted. Just as long as it's in the right proportion. Jonathan's prize antique car is 115% of last year's value. So of last year's value, so we'll make last year's value be the 100%. And this now, his value is 100% plus 15% more to make it 115%. The car is worth, so now we're doing less than or more than, so we want the difference. The difference is 15% over, now do we put it over the 100 or the 115? So we go to the question here. The car is so much less than its current value. Well, that's the old value. That's the current value. So we have to do this by 115. So 15 divided by 115 is 13% goes in there. So the car was worth 13% less than its current value. Current value has to go in the denominator because it ends with its current value. Hopefully, these three problems were caused a lot of problems for you. So I hope that makes sense. Number 4, 28.5 million. 25.8 million. Looks like that. Pounds of beef is consumed in the U.S. in 2010, in 1 year. Each head of beef is 650 pounds. And we're trying to figure out how many heads per hour. This is pounds per year, so we got to get to heads per hour. So we need heads to show up. And pounds to disappear. And it turns out 650 pounds is one animal, one head, as they call it. And we have 1 year, and we got to get per hour. So we need to get the years to cancel. And that's 365 days is 1 year. And then we need to get the days to cancel and get it to hours. And that's 1 day is 24 hours. And this, what I told you to assume, caused people some question about significant digits. There's 3 in this. 1 year is exact. 650 is only got 2 significant digits. 365 has got at least 3, and I said assume it's got 4. And this is exact. So that means of the ones that have significant digits, we have 3 here, 2 here, 4 here, and 2 exact, so a lot there. So if we got all these and we're multiplying or dividing, you go by the number of significant digits in the smallest number of significant, 2. So once we work this out, 25,800,000 divided by parenthesis 650 times 365 times 24. Those are all in the denominator. So I put them in parentheses. I press enter, and I get 4.531 whatever, but I can only use 2 significant digits. So I get 4.5 head of cattle per hour. Only 2, because 2 was the least significant digits. Okay. All right, now we got this 73 billion, million, thousands, ones. And that's dollars. And we're trying to get the height in kilometers. So we need the dollars to cancel, and we know that $10 is 1 millimeter. And then we need the millimeters to go. and a milli means 1,000, so it takes 1,000 millimeters to make 1 meter. And then we need to get the meter to go to get to kilometers. And it takes 1,000, because kilo means 1,000, meters to make 1 kilometer. And let's look at our significant digits. 2. This has only got 1, but they said, so that's weak. That's got 1, that's got 1. So our answer should probably be only 1 digit. But let's see what we get. I didn't say to consider significant digits on this one. But 7, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, divided by the 10 and the 1,000 and the 1,000. By putting them in parentheses, all 3 of those are dividing into that, or it works that out, and then it does division. And we get 7,300 kilometers. And if I were doing significant digits, this is a multiplication, division. These are exact, so that even though I said 1, those are exact, so those can be infinite number of digits. This one is not exact, so there's 1 significant there, 2 there. I should only do 1, so I should say about 7,000 kilometers. But I accepted that for full credit. All right, more significant digits here. 1, 2, 3. 0 is between numbers, so we keep it. So that's 3. 2, 2, 4, 0. Well, that 0 is not pushing the number either way. It's kind of hanging on the end, so we count it. 4. This one, the zeros are pushing the 4 over, so they are not counted, just the 4, so it's 1. Okay, so it's the next decimal place that is the plus or minus. So 005.005, but this is in a number that's times 10 to the 5th, and so this is. Now if I multiply this by 10 5 times, it moves the decimal 1, 2, 3, 4, 5, and makes it 500. That's plus or minus on this number that is 7. Move the decimal 1, 2, 3, 4, 5. That's what this number is. So the implied error is 500 divided by 708,000 times 100, which is 0.07 percentage error. Implied. Now this one, that one counts, so it's the next one, 005. So it looks kind of like the same number. It is not times an exponent, so it is just this number. And so if I want the percentage error, I take that, 0.005, and divide it by 22.40, and then times 100, and it's 0.02% error. Both of these are really precise, very small error, not even 1%. Now the last one, which has only 1, that's the last significant, so that one's plus or minus 5, 0. So this one's 50. That's plus or minus. And so we would take 50 divided by 400 times 100, and we get 12.5%. So there's quite a bit of error in that one. So that's 6, and then 7 says, look at these. and tell me which one is the most precise. Well, the most precise is the least error in it. So that would be B, or the 22.4. And it's got the most significant digits, or smallest percent error. Either part of that. And which one's the least? Well, that's C, because it has only one, or it's only one significant digit, significant figures, or if you wish, the fewest significant digits, or the largest error. Okay? Several things you could say on that. Okay. Area of a rectangle. So normally you would just multiply that. So that'd be 49.5 times 71.25.45. That comes out to be 3536.775. But we're multiplying, so you use the least number of significant digits. This number has 3, this has 4, so we round it off to 3. 1, 2, 3, this is bigger than 5, so we make it 3540 meters squared. B, when you're adding or subtracting, 21.20 minus 5.3059, we get 15.8941. But when you're adding or subtracting, you go to the last decimal place that had significant digits. This one was tenths, hundredths. This went further, so we'd only go to the least one, which was hundredths. So we have to round off to the hundredths. When we look at the next digit, it's less than 5, so we just drop it, and we write 15.89 yards. So use the estimates for these and use the implied error of the measurements. So this is 29.3, and we're looking for the minimum, the lowest possible. So it's measured to this place, so it's plus or minus 5 there. So we'll take the 29.3 minus 0.05 in the next place, and we get 29.25 times, but there's only 3 digits, so our implied error we're going to be multiplying, and they all have 3 significant digits, so our answer will be 3 significant digits. But we're going to use this number as the low ball for the implied error, and this one is going to be also minus 0.05, because the next digit would be in that place 0.05. So we're going to go 40.0 minus 0.05, and we get 39.95. And this will also be in the next place, so it's 18.1 minus 0.05, which is 18.05. And so this will give us our lowest possible error. And remember, we got to go to 3 significant digits because that's what each of those had for the least. And so that's the leastest number of significant digits. So even though I'm using 4, we go with our original numbers. 29.25 times 39.95 times 18.05, and we get 21092.10188, but we don't report all that. We only do 3 significant digits. 1, 2, 3, that's bigger than 5, so we round up. 21100, and that would be centimeters times centimeters times centimeters, centimeters cubed. All right. 10. Complete the table. So there was 40,000 people. So these are our totals. And where 6,000 have the virus. Does have the virus, does not have the virus. So has the virus, that's got to be 6,000 total. So that means 34,000 go here. Now it says incorrectly diagnoses a virus present, so that's a positive test, when the patients don't have the virus. Doesn't have the virus, 4% test positive. So we want to do 0.04 times 34,000 that don't have the virus, 4% of them test positive. 0.04 times 34,000. So that's 1,360. And if I subtract those from the 34,000, I know that the ones that it does correctly are 32640. Okay. Now it also says that the same test also correctly predicts 97% of those that do have the virus. So they do have the virus, and 97% of them test positive. So 97% of the 6,000. Let's write that in there. They test positive when they do have it. 0.97 times 6,000. And that comes out to be 5,820. The rest, so that subtracted from 6,000 is 180. Meaning over here, the totals that test positive are the 5,820 plus the 1,360, plus the 5,820 is 7,180 that test positive, and 180 added to this, 32640 plus the 180, there's 32820. Those are our totals. Now B, what is the chance of someone testing negative? Testing negative. Of all that test negative, that would be this way, not these. These are whether they do or not. Of the testing negative, So of testing negative. So that makes it our denominator. 32820. Having the virus. 180. So that's 180 divided by 32820 times 100 to make it a percent, and that would be 0.55%. Okay. Find the percentages for the cure rates, including overall. So we have 22 divided by 120, which is 18.3%. We have 46 divided by 80, which is 57.5%. We have 20 divided by 120, which is 16.7%. We have 100 divided by 180, which is 55.6%. Excuse me. And then overall. Well, that would be 22 plus 46 is 68 out of 120 plus 80 is 200. So 68 divided by 200 is 34%. For drug B, there was 20 and 100. That's 120 divided by 120 and 180 is 300, which is 40%. So that's the overall. So can we make an argument using our numbers here that A is better? Well, for men, A is better. For women, A is better. Percentage. 18.3 is greater than 16.7 for men, and 57.5 is greater than 55.6 for women. There's my mathematical argument for why A would be better. And C, give numerical evidence that B is better. Well, we can just look at the overall. And overall, B is 40% effective, which is greater than the 34% for